So people have asked me some questions here. This might apply to you. Again, what I'm trying to do is I'm trying to get all the data we had from the data set. Here, let me show you what it looks like originally. Right? So this is the StatCrunch version, but we had 3 columns of data. Smoker, ETS is exposed to smoke, and what's the last column? No exposure to smoke, right? No exposure to smoke. So we're trying to get those 3 columns into one because that's how Excel works for this particular test. Now why I keep doing that, I have no idea. Let's go here. Don't do that to me. There we go. Hang on. So again, oh, Russell, you asked me, how do you get this ETS to show up everywhere? Okay. One thing you can do, guys, is you can go on top of it and you can right-click, and it gives you lots of options. So I might copy. Okay. And then what I'll do is I'll highlight everywhere I want to copy it, and I'll press Enter. So if I want to copy it all the way down to there, now I press Enter. That takes care of it. Is that up? Okay. So now we want to do the same thing for no exposure to smoke. So let's see. The no exposure to smoke column, here's my data. This time I'm going to choose Cut, because I want to actually move it. And I'll go all the way to the bottom. And there it is. Oh, I have to type in NOETS. No exposure to smoke. And let me copy that all the way down. And so I have a huge column. Okay? Well, some of this is just I'm trying to get you guys comfortable with working with a computer. You know? You're going to walk out of this class. How much statistics will you use throughout your career? I don't know. Will you want to be using a computer? Yes, that you will. So there is something to what I'm trying to do here for you. To develop some level of comfort using the computer is definitely worthwhile. So anyways, to do this particular exercise with Excel Stat, and again, I have to launch mine still. It's not running yet. But you want to click on, if you have the full version, I believe it's under modeling data or mathematical modeling of data. But you want to click on ANOVA, which stands again for Analysis of Variance. So here it is, ANOVA. And let's see, it asks me, where's the quantitative data? What the heck is it looking at? Am I on the wrong sheet? Oh, it moved sheets on me. So you have to find the sheet where you have all the data. And you want to choose all the numbers, right? Do you guys see what I'm doing? I'm trying, but I have no idea if you follow what I'm doing here, guys, from your facial expressions. No clue. See what I'm doing? I'm highlighting every number in that column, and I'm saying that's the quantitative data we're dealing with. You guys with me? No. When you click on ANOVA, you guys should see this menu. It should say quantitative data. So you want to select it.
What would ANOVA be under?
Oh, under modeling and regression, mathematical modeling. I just had it by itself, ANOVA, right next to linear regression. You did find it or did not?
Now I did.
Okay. So we have all this highlighted, quantitative data. You need to fill that in. You gotta tell it where the data is. And you'll notice down below it says qualitative. That's what I'm going to highlight next. I'm going to tell it where the labels are. Now again, I have to make sure I'm on the right sheet that has the labels. And there's all my labels. I'm going to highlight all those. Again, trying to do this without a computer would be crazy. With a computer, though, we can do some amazing things. So once you guys get that highlighted, then you're going to press OK, and you will have a little report come up. All right? Russell, I'll be right there. I press OK, and I get a huge amount of information, but really, there's really only a little bit that's kind of relevant to us, right? Do you remember the name of the distribution that's used when you do the this particular test, the ANOVA test? The name of the distribution. It's not the normal distribution, and it's not the T distribution. It was called the F distribution. And you might remember the F distribution is one-tailed. It only goes to the right. And so what we really want to do is we want to look at, are we going to reject or fail to reject the null hypothesis? Again, the null hypothesis in this chapter 12 has to do with three means. I wrote this down yesterday for you guys. Are the means equal? Right? That's the null hypothesis. I guess the alternative hypothesis would be that one or more are not equal. Okay, so that would be my alternative hypothesis in general. Anyways, in problem 16, they asked me to test the claim that the three samples are from populations with the same mean. So again, smokers, non-smokers, secondhand smokers, right? Is it true that they're going to have the same mean, or can we reject that claim? That's really what I'm asking, right? And so what I need to do when I run this report, I need to find the p-value, okay? I mean, there's a lot of things that get spit out because they don't know what information you're going to want. But you want to scroll down until you get to this analysis of variance chart. And right here, that is the value of the test statistic. F. F equals 20. Right? That's really far to the right for an F statistic. Matter of fact, right next to it, what's this right here? That's the p-value. It's telling me the p-value is less than 0.0001. The p-value here is very low. Therefore, the null must go, right? And so, in particular here, we could say that these do not necessarily, well, we can say that we have sufficient evidence, right? Anytime we reject the null, we're going to start with that. So let me go to the paper again and write down exactly what I want to write. Okay? So again, we got F equals 20. The p-value is less than 0.0001. Okay, so we would reject H naught. And so I say, there is sufficient evidence to reject the claim that the three populations have different means, or do not have the same mean. Now, I think that the other question they ask is a little bit trickier to answer. Oh, I'm sorry, you can't see the final conclusion. There it is. I think the other question they asked was a little bit trickier to answer because they asked, look at the last question. It says, what do the results suggest about the effects of secondhand smoke? Now, isn't it true that secondhand smoke was really only one of the three columns? I mean, maybe that mean is the same as one of the other two. I don't know. This is a three-way comparison, right? We're asking, are all three means the same? That we say no. So you might have to do a little further analysis to figure out exactly what. I guess, a cursory look at the values, right? Let me go back to StatDisk where we had that, because I wanted to show people how to use the StatDisk also. So if you look at a cursory look at the values, yeah, there's a lot of zeros in the last column. Very few zeros in the first column. The middle column, yeah, it's interesting. You'd have to do some further analysis, I think, to say how much secondhand smoke affects you. Okay, but it's clear that the first one does. Smokers are effective. Yeah, just to show you what else we can do here. So this is StatDisk. Some of you are going to be using that for your project. And if I click on Stats, right, down here I have an ANOVA chart. And we're doing a one-way ANOVA test. They cover the two-way later in the chapter. But one-way ANOVA. And this is really nice. You don't have to stack any data. You just say, hey, which columns do you want? Smoker, exposed to smoke. So these three, I guess I will highlight all three by using Shift and then clicking on them. And if I just say compute, I think it'll work. So here's my ANOVA table. Once again, my F value is 20 and my P value is really small. And so we would reject the claim in a very similar fashion. Okay. Yeah, StatDisk is very nice. I mean, it's definitely written for this book. On the other hand, Excel, I would say, is more powerful in a sense. You get more information, but this is nice and clean, which is cool. So 11.2, page 567, really 566, I guess. Okay. So it's goodness of fit. What a great word, goodness. So what we have here is a brand new statistic, guys. Ha-ha. You guys seen that letter before? So let me try it with you here, if you're taking notes here. This guy here is the Greek letter. You make it with it's an X with a little curl here, and it's pronounced chi. Usually people write CHI, but it's pronounced chi. And chi squared is what you call this, chi squared. Remember, we just had R But when we wanted to talk about a proportion of the data that was the linear regression, what did we do instead? We did R squared. Sometimes the square is actually part of the statistic. Probably the first statistic that I ever studied intensely, chi-squared, comes up all over biological sciences, medicine. I can remember being in a genetics classroom and we had to do chi-squared analysis. And at the time, guys, I wasn't even a math major. I had no idea what I was doing mathematically, but I did know how to do the tests, okay? So this is called chi-squared, and some of you may see it again. And so, if you show up and you say, oh yeah, the X, they're going to say, what? Haven't you ever had statistics? And you'll say, oh yeah, I took it with Zachlin. Who? Paul Zachlin over at Lakeland Community College. Please make me look good by knowing that that says chi-squared, okay? Here's the formula for it. Do you guys know what that means? It's been a while. Do you know what that means? Sigma, yeah. The capital sigma, what does it mean? So we're adding lots of stuff up. It stands for sum. It's the big S, right? We're going to add a whole bunch of things together. All right? And so the O and the E are very intuitive, I think. O is observed frequency, and E is expected. Hey, wait a minute. We've used that word before, expected, but it's been a while. It's back in chapter 5. Do you remember what I said? Expected what? What's that? So O is observed. Yeah, we've had lots of observations. You're right, even in chapter 12. But E, expected. No? It was when we were doing probability. Yep. And we called the mean, maybe you don't remember this. The mean was also called the expected value. Do you guys remember that? Vaguely. The expected value, what we usually did was n times p. N was the number size of your sample, and p was the probabilities there, you're right. So we had this idea of an expected value. I remember we were rolling 2 dice. Do you remember what the most common number to roll was when you rolled 2 dice? Right, anything between 2 and 12, but 7 was the most common. And we actually computed the expected value was 7. So there's kind of a lot behind this, I guess. But the idea is to figure out if you're getting what you expect you would get. Okay? And so I almost think, running through an example is probably our best bet in terms of understanding this. So, I guess the World Series comes to mind. Yeah, let's do that one. I just love baseball, so we have to go there. Problem 17 on page 575 is what I thought I'd attack with you. Okay. So let's see. Unless you guys prefer Kentucky Derby, we just had it. Did you guys watch?
I've heard.
Anybody? No. Baseball? We're going baseball. All right, so let's go World Series. Tribe lost last night, by the way. A walk-off win for the Blue Jays. Kind of sad. But here we are. Table below lists the number of games played in the World Series as of this writing. So you guys know how the World Series works after last year. Whether you were a baseball fan or not, you got sucked into it, right? The maximum number of games you can play is 7. Indians lost in Game 7. The minimum number of games that are played in a World Series is 4. Because as soon as someone wins 4, they win. So someone could... One time the Indians got swept in 1954 by the Giants. That's the famous Willie Mays catch that started the whole thing. Anyways, sometimes the contest lasts 4 games, 5 games, 6 games, or 7 games. And I guess what we're doing here is we're looking at a chart that shows those four possibilities. It shows how many World Series lasted that long. By far, which one's the most common?
Looks like 7.
Oh yeah, 7 games. My wife's grandfather had a theory about this. He's passed away now. He thought all pro sports were totally fixed. Oh yeah, when he said Game 7, like if he had been alive now, he would have said Indians, Game 7, 9th inning. He would have said figures. I mean, he would argue that they're probably just throwing meatballs, letting these guys hit it out to catch back up. I mean, he put pro baseball right alongside pro wrestling. You know? Oh yeah. I mean, I know. But he was convinced that there's something to this. Now, when you look at this, down below we listed the expected proportions. I think I should remind you where those are coming from, because we haven't done probability in a while, right? But here's the thing. Look, what's the probability of us winning a baseball game? Well, let's suppose we're at exactly same ability level as the Chicago Cubs. Let's suppose that on any given night, the chances of winning are 50%, right? So then the probability of me winning that first game would be 1 out of 2. Right? Now, if we win, you play a second game. Say we lose. If we win, we play a third game. Now, do we play a fourth game? Yes, automatically, win or lose. But let's suppose this happened. Win, lose, win, win. Right? Would you play a fifth game? Yeah. Because we won a game, lost a game, won a game, won a game. But let's suppose we win. We're done, right? We're not going to play another match. Now, if you lose, right, the only way this is going to happen is if the score is at tied 3-3, let's say. Okay? So when you think about it, you're automatically going to play, let me show you. You're automatically going to play 4 games. And so at the end of 3 games, I guess there's 8 possibilities. And at the end of 4 games, I guess there's 16 possibilities. Right? So when you look at the end of 3 games, I almost think this is where you start. Okay? And you say, what's the score so far? Well, it could be Indians 3, Cubs 0 after 3 games. It could be Indians 0, Cubs 3. By the way, it was not either of those, was it? Does anyone remember what it was?
It was 3-1, right?
Well, eventually it was 3-1, that's right.
Oh.
At the time, it was Indians 2. And then we did win the next game, you're right. Cubs 1. Or it could be Indians 1, Cubs 2. Right? Now, there are 8 paths here. 8 little tree branches that I'm looking at, right? But I want you to understand something here. If it's 3-0, there's only one path where that would happen. That would be if we won all 3 games, right? This is 1 out of 8. If we lost all 3 games, that's only 1 out of 8. Now, there are 6 other possibilities. 3 out of 8 would give you this route, and 3 out of 8 would give you that route. Do you guys see what I'm doing here? I'm giving you kind of a list of all the different possibilities. Now, could it be that the series is done in 4 games? Well, if we're here, no. The series will not be done in 4 games. I guess you could argue most likely no. What if we're here? Could the series be done in 4 games? If the Indians got one more win, right? What's the chances of that happening? 1 out of 2. 1 out of 2 times 1 out of 8 is 1 out of 16. Now, there's another way, okay, and that's right here, 1 out of 16. But the chances of it going beyond, I guess, would be 14 out of 16. Right? Are the chances that it goes more than 4 games? Okay, that's enough probability. I wanted to review that so that when you look at the chart and you see that the expected proportion of series that should be 4 games, you could see where they got 2 out of 16. The other probabilities are found very similarly, okay? It just takes more work. Does that make sense to you guys? Okay? So now the question is, are we getting what we expect? I mean, do we expect to get more 7-game series than 4-game series? Absolutely. And we are getting more, right? Do we expect to get more 6-game series than 4-game series? Well, yeah, we do. Are we getting more 6-game series? Well, we got 3 more. Is that enough more for me to think that it's following the expected probabilities, or am I starting to say, the model might not be quite right? Well, again, you guys know the story. This is where it comes down to things like, hey, Paul, what's the significance level? What's the critical value, right? Chi-squared is the test statistic. Chi-squared measures in ratio format how far away is O from E. That's what this really says. If the observed is exactly the same as the expected, you get 0. So chi-squared, you guys, the picture of chi-squared looks a lot like the F distribution. I'm going to turn to page 581 for 1 second here, and then we'll come back to our problem. Page 581, again, it's not the same as the F distribution, but it is true, again, that it starts at 0, right? So you guys have seen this kind of distribution. See, in this particular, I don't know what this example is, I didn't read it. But in this example, the test statistic chi-squared was 58. The critical value was 7.8. So they said, oh, wait a minute. Our model's wrong. That's really what it's coming down to. Is your model correct or is your model incorrect? So, let's go ahead and work this out. You guys have the calculator? Okay, so what we're going to do is we're going to use the calculator and we're going to input the possibilities here and we're going to perform our goodness of fit test. If I remember right, we used matrices for this, which we haven't done yet, so this should be kind of a cool way to end the course. I know it's used for 11.3. We can just put it under stat, so that's actually not bad. Enter the observed frequencies in list 1, and then identify the expected frequencies and put those in list 2. So this works out really nicely. Let's go ahead and do this. I got to launch my calculator first. You guys know how to put these things into lists, right? So if you wouldn't mind, while this is loading, go back to page 575. Put the data from each row into a column of your calculator. Right? So I'll punch it back up here so you can see it again. So you want to put these numbers into the calculator. Okay. So here's my calculator. Guys, I'm going to press the stat button. I'm going to edit a list. And so Boy. Okay. I guess I have to clear out a couple lists. Remember how I do this, guys? I go on top of L2. I press Enter first. Then I delete it, right? Otherwise, it'll just... And then I press Enter one more time. Otherwise, it'll just be, gone. I'll go on top of L1. Enter again. Clear that out. And I'm ready to use the calculator for this chi-squared test. Here we go. The actual World Series contests, there were 20 that went 4 games. There were 23 that went 5 games. There were 23 that went 6 games. And there were 37 that went 7 games. Now more, because we had one 7-game last year. And the expected proportions, guys, you can let the calculator do the math for you. If I type in 2 divided by 16, it'll work out that that's 0.125 for me, okay? So then I'm going to type in 4 divided by 16, 5 divided by 16, and 5 divided by 16. So there we are. Amy, you all right?
Yeah.
Okay.
No, I'm fine.
This okay?
It's not this, yeah.
Okay. So I have the data in the lists, right? And I'm ready for my goodness of fit test. And again, hey, you guys tell me, where do you think it probably is? You guys know this calculator enough now, huh? All these tests, where do we find them? Yeah, hit that stat button, right? And over here to the right, you guys want to select tests? Okay. Goodness of fit, I'm going to hit the up arrow because I think it's one of the last ones on the list. Yeah, you see C and D here? This chi-squared test is a different test, guys. This is the one I want, chi-squared goodness of fit test. So that's choice D on our This thing has so much in it, this calculator. Oh, 2-sample F test, very interesting. We're just doing F tests in the other chapter for ANOVA. You could do ANOVA here too, I guess. Okay, let me make sure I have things in the right list. Observed, list 1, is that right? We did put, yeah, we put the games, the actual games were in list 1, and we did put the expected in list 2. DF stands for? Okay, so what are we going to do for degrees of freedom? Well, once again, it's, remember n minus 1? So n here is the number of categories that you have. So how many categories do we have? No, 2 is the number of lists we have. Categories tells you like how many different possibilities there were, right? So we said it's either 4 games, 5 games, 6 games, 7 games. I'm counting 4, so I'm saying degrees of freedom is going to be 3, right? Now I'm ready to calculate, and let's see what we get. So it tells, wow, look at that chi-squared test. Chi-squared equals 11,000. In the one in the book, I think it was like 75, right? And the critical value is about 7. So this is telling you that what happens in the World Series is not even close to what would happen if you flipped coins. But if you think about it, that kind of makes sense. Why? Is the probability of winning a game really 50%? No. Actually, part of this comes down to baseball. I don't know if you know. Did you know that being the home team is a huge advantage? Why? You get to bat last. And so you can see everything that just happened and you can make decisions, right? And so you will find that home teams tend to win more. Well, look last night. Toronto beat us in the last inning, right? I mean, I would argue that that is one of the reasons that the games take longer than probability says they should, okay? Because, as a matter of fact, they switch back and forth who the home team is, right? And so that's one of many factors, I think. Who knows? Maybe Grandpa Caserta is right on that one. I'm not sure. Do you guys have any questions about goodness of fit? No? Let me pause here for a second.
Chi-square